Okay, so we're going to move on to our next topic, and we're going to spend a lot of time on this next set of things. So networking. And I thought before we talked about, so next we're going to talk about how to make TCP servers. I thought it would be good to review networking. I hope some of this is review. If it's not, you're going to be pretty lost. But that's just life. So I don't know what to tell you.
It's true. The sound is so cool.
So, networking, I'm going to review it, and we're going to walk through what happens when you visit a URL in your browser. Just going to review the whole process, and then we're going to build a piece of that process, right? The idea is that it all involves protocols, lots and lots of protocols, okay? And the idea of a protocol is the agreed upon conventions between two parties when you're communicating. It's the rules of that conversation. And maybe the easiest analogy would be mailing a letter, okay? Now this analogy in 10 years will probably be obsolete. But as of right now, everybody has mailed a letter, so it still works. The idea is that you have your envelope, right? And you put your return address over here, and then where it's going to. So we could say, this is the to, and this is the from, and then you have your stamp, etc. Okay? And inside of your letter is like a letter, right? To whoever. And you have your message, and then at the end you say, from so-and-so, or whatever you say, okay? And what's important about this is this protocol, the conventions for the definition of the envelope, the format it needs to be in, this being here, that being there, the stamp, all that kind of stuff, is the protocol the post office uses to figure out how to get your mail to whoever you're sending it to, okay? The post office does not care what is inside of the letter. I mean, they kind of care because you're not allowed to mail certain things, but in general, whatever's inside of your envelope doesn't matter, right? Okay? And in a similar way, when we talk about protocols for networking, it works this way as well. They're at different layers, okay? And so some layers care about this, and some care about that. And so it's very important when we're talking about networking to make the distinctions between those layers. Because in web development, we work at certain layers, but we don't work at others. For example, we work at the HTTP layer, but we don't work at the Ethernet layer, okay? We don't care, like the physical transfer of bytes and stuff. That's interesting, but that's not something we have to interact with. We're not building network cards, so we don't actually have to care that much about that. In other words, however my letter gets to where it's going, not a big deal. I care about the content of it. Okay? And so we'll see some examples of various protocols we use with networking, but I just want to give this idea of the envelope. Okay, everybody following the envelope? Okay. Hopefully that's not too confusing. We'll use it again in a second. So here's the Osi Layer Model. Okay, think of this like an onion or something. And the idea is that there are lots of layers to a network stack. And they sort of build on top of each other. So at the most basic level, you have a physical connection between two machines. I have my laptop. It has this Ethernet Cat5 cable connecting to a router or something. And then eventually that connects to your computer over there somehow. And so there's this physical description of how that works, okay? And so that's like the bottom layer. Like I said, we generally are not that concerned about that. But there's a protocol that governs the communication between those devices. Above that, we have a data link layer, and that might be, I think it's Ethernet would fit in there. And then we have network, okay? This is IP, Internet Protocol would fit in here maybe. And then above that's a transport layer, and then we keep going up the stack. I think the definitions here start to get a little shaky of what fits in which bucket. But the basic idea is that we tend, as web developers, to work in this layer above. We're not so concerned about the layers down here. Okay? The other thing to know about networking, is everybody following the basic structure here? Yeah. Okay, and the other thing to recognize here is that once we get to like this layer and above, things start to be nested within each other. It's like Russian dolls. You open it up and there's another Russian doll inside. You open it up, there's another Russian doll. And that literally is the case. these are sort of packet switch networks, and what that means is that you break up messages into small packets. And the packets each have within them, so if you imagine we had that letter, there would be a top part here, and let's say this is the IP header. And there's a bunch of information in there that's used at this layer. And then above it is a TCP header. And there's information that TCP uses there. And then above it is an HTTP header. And so there's information that HTTP is using in there. And then maybe in here is a cat photo or something, okay? In other words, the thing that we're interested in. But there's all these other headers above them that's being used as part of the payload, okay? That's coming with the packet. And each of the protocols uses those different layers, okay? Everybody following the idea of it? So imagine an envelope that has another envelope inside of it, that has another envelope inside of it, and then each layer is picking it out using the information it needs along the way. So these are packet switch, which means when you send a message, it's broken into small pieces, and then each of those pieces is sent through the internet to its final destination. So every IP packet has a source and a destination of where it's trying to get to. Okay? And so when I make a request to a URL, so if I go to my browser and type Google, that's going to involve a message sent to a Google server that will be broken into many pieces and then routed to their server. And then they'll send messages back to me, and they'll come back to me so that I can see this page. And so imagine what you're doing there is you're breaking it up and then mailing a whole bunch of different letters. The post office figures out how to get it to its destination. And then on the other end, he's like putting all the letters back together so that he can understand what you sent. And then he's writing a letter, breaking the pieces, sends it back to you, and you get it, okay? And that's how the internet is working in general.
So one email message could have taken like 8 different paths, the different pieces. If there's 8 pieces, could have gone 8 different paths to get to my computer, and it's pretty simple.
That's right, yeah. That's the idea. So that's the OSI model. And basically what I want the takeaway is there's IP, and then there's TCP, and then there's HTTP. We generally only work up here. We work a lot with HTTP, a little bit with TCP. Pretty much never with anything below that. Okay? But I wanted to show you the idea of the whole stack.
What does OSI stand for?
Oh, the
Open Source Infrastructure or something?
Open Systems Interconnection Model.
Open Systems Interconnection.
These protocols get very, very complicated.
Yeah.
TCP is a very nuanced and difficult to understand protocol, and it's the basis of everything we do on the internet, but the point is you don't actually have to understand all the technical details to know how to use them. And that's the power of an abstraction. You know,
Just a little sideline question.
Yeah.
Where do the hackers work?
They work at all the layers.
All the layers?
You can hack at any layer. You can hack the physical connection, you can hack the, it doesn't, yeah, so there's different, you can
Well,
take
I'm talking like, say, the guys that are really trying to get into, say, the government databases and stuff. Say this latest attack that they say came from China. What layer was that you received?
Let's see, the one that resulted in all the confidential information being released was not even really a hack. What we did is we hired an engineer in China and gave them root access to our machines, and then they just gave it to the Chinese government. We can call that a hack, but he didn't have to do anything. So,
Okay. Oh, wow. Okay. So it's easier than.
the point, though, most hacking is social engineering. It's getting somebody to release information they're not supposed to release, and then taking advantage of it. In other words, it's an error, it's a human error, not an error in the protocol per se. Now, there are errors in the protocol. That does happen. But in general, the easiest way to hack somebody is to get them to release you information they're not supposed to.
That's why you get those calls, like, or your grandparents get those calls from Microsoft if they need help with their computer.
Exactly. And then you press a button and you've given them credentials or whatever. Okay, so so that packet switch idea, maybe I'll draw a diagram so you can see it, right? So I have my computer over here, right, and it's connected to a router, or something, and this is connected to the internet, and then the internet is made up of lots of machines, okay, that are all interconnected. And it figures out all of these, and in the end, it's Google over here or something. A route to it. That's the idea of the packet switch there. Okay. So when I send a message, it gets put into this, and eventually gets its way over here. Now, the protocols that govern this are routing protocols that govern that, and we don't have to be super concerned with those. But just notice. All of the programming we do is built on assumptions about the abstraction. We work on an abstraction. Okay, I send messages over TCP. Now, how TCP is actually implemented is not that significant. To give you an idea of what I mean, I'm connected via physical connection to a router. You're using Wi-Fi. So the protocols that govern that communication are different, very different. The way Wi-Fi works and the way physical Ethernet work are very different concepts, right? Radio waves and I mean, I don't know how they all work technically, but they're different. But the protocol above that layer, the protocol that's the internet protocol, is exactly the same, okay? And so we can work on the abstraction without having to understand how Wi-Fi and Ethernet work, okay? And that's the idea, is that the abstraction free us to be productive, yeah?
The interfaces with the database.
It's exactly like the interface.
Wi-Fi, hard cable, either one can plug in.
Yep, exactly like the interface. That's exactly the same. It's an abstraction. We work with the abstraction. Okay. Some people talk about how, oh, you're making an assumption and that's like a really bad thing to do. But the truth is, it would be impossible to write software without assumptions. Okay? We just have to assume that TCP works. Because otherwise, it took, decades to make TCP. There's no way you could do it yourself. I mean, so we just have to assume the layer below us is working. Sometimes it doesn't, and we discover that, and it sucks, but we sort of have to make that assumption to be productive, okay? And part of what it means to be a software developer is being comfortable with not understanding everything you're doing. You're always in sort of this wishy-washy territory where, oh, I know HTTP, I have very little knowledge about this, but I can still be productive software developer, okay? Because it's impossible to know all this in technical detail.
That's cool to hear you say that.
Okay, so let's take an anatomy of an HTTP request, because I think it's kind of fun to think through how it all connects together. So when I enter that URL into my browser, the first thing it's going to do is, well, I mean, it may do a lot of things, but it has to look up google.com, and it uses the domain name system to do that, okay? So that www.google.com is mapped to an IP address, okay? IP address meaning that IP protocol, they have addresses that are from and to destination. Every computer on the internet has an address. And so Google's server, somewhere out there on the internet, has an IP address. And it's mapped using the domain name system. So google.com gets translated into that IP address. We can find that out in several different ways. The easiest is a tool called dig. So DIG, I don't know if it's on Windows, it might be. And you give it the domain name. And it gives you information from the domain name system about addresses and things. So it tells me that these are all the IP addresses associated with Google. Okay? So A means an address, IPv4 address. And here you can see its address. So you'd see 4 numbers separated by dots. Okay? And so going to google.com is as if you went to this address. So that's the first step, is take a domain name and turn it into an IP address, and then go to the IP address, okay? So the reason I bring that up is DNS is a big part, is an important component of web development. If you're gonna make a website, you probably need a domain name. You don't expect users to enter this. Okay? You expect them to enter an English word, right? Some sort of name, or something like an English word. So how do you get a domain name? There are people who sell them. Registrars. I'll give you one called Namecheap. I like them. They have a nice, clean interface and stuff. You can go to here, look up a domain name and buy it. It costs $10 a year, about. And every year you have to renew it. Don't forget to renew it or you'll lose it. but you can buy one. And then the next step is you have to associate that domain name with what's called a name server, okay? And the name server is the guy who is storing this information. So Google.com is associated with a name server, and that name server has these listings, has these addresses defined, okay? Yeah?
In terms of buying a site name, domain name, those companies selling it, are they buying those names, like the rights to the names and then selling them? And if they are, like who are they buying them from? Like where's the source of these domain names coming from?
Yeah, so there is an organization called ICANN, ICANN, the Internet Corporation for Assigned Names and Numbers. I don't know all the, there's been sort of a back and forth, and this has been changing. It used to be the case that there was I think a consortium of companies somewhere in California that ran this, and I think they've been trying to make it more international because they were afraid that it's too US-centric or something. But so I don't know the details of how this all gets run. It's kind of complicated. But they're responsible for making it so that registrars can sell the domain names available. Okay. But the basic idea is that domain names are set up in a tier hierarchical relationship, and it's based on the name. So if I have com, underneath com is Google, and basically there's this ICANN that's running com, and Google sort of under that, and so on. Okay, and there are international, right? If I go to .co.uk, there's something in the United Kingdom that runs that. And it's up to a country to define how it decides to run its domain names. But in the US, we have this structure where you can get them from registrars and all that. You can usually buy domain names for other countries. They'll sell them to you. So a lot of people use, for example, .it because it has this nice English whatever .it, right? You can say something like that's like an Italy, okay? Or there's Indian Ocean is commonly used. Yeah. Which is weird, right? You would think, oh, .io. It's like, yeah, that's like actually a country. But we use it because it has this nice. But anyway, so you can get registrars that sell these various domain names. But like I said, they're about $10. They're not that expensive. So usually it is if you come up with a clever idea for a domain name that's not taken, just buy it. Right? Impulse buy that sucker because you never know. It might get taken. So there are rules that you can't like. In the early days of the internet, like if you bought Coca-Cola.com, you were not allowed to keep that. You were not allowed to make Coca-Cola pay $1 billion for that domain name or whatever. But in general, you can own any domain name you want. So like I said, you have that name server. So also the service, those are different services. Most registrars also provide the name service capabilities. But there are other companies that also provide them. So here's Cloudflare. They're super useful, okay? And they will do this name serving capability for you. They also provide a lot of other capabilities. I'm not going to log in. But anyway, you would see on their list of your domain names you have associated, and you can add those records, okay? So you might add your A record. How do you get your A record? Well, it depends on your service. And I'm not going to show you that because we're not creating our own, we're not using virtual servers, but that would be typically what you would do. Maybe you go on Amazon, spin up a server, you'd get its IP address, throw it into Cloudflare, and that's how you'd hook up the two. But we're going to be using App Engine, and I think they allow custom domains, but it's a little different. But I'm not going to show that. So once we have our IP address, what's the next step, okay? So then we're going to speak HTTP. Now you guys have seen some of this, right? So I go to google.com. If you hit Command-I forget what it is in Windows, but you go up here, more tools, developer tools. And this opens up this guy. This is a little hard to see, but you have your net tab here, and it shows the requests that the page made via HTTP, via the HTTP protocol. And so we can look at one of these. You know, I'm going to change to look at golang.org because Google's front page is like absurdly optimized because they get so many hits. Okay. So down here we can see all the requests made on golang.org, and you can see the HTTP details. Now we're going to talk more about the HTTP protocol because, like I said, this is the web developer bread and butter. This is the world we live in, is this world. And so we'll see way more about the details of this protocol. But you can see the HTTP details here. And so this is a good place to go if you're trying to debug headers, if you're trying to debug the data you get back directly. You can look at response, and you can see HTML, right? But if we look at CSS, you'd see CSS in here. It's whatever the server returned, and other things. But that is our first go-to resource. You use the net tab a lot for HTTP debugging, okay? The other thing you can do is curl. I think I showed that before. Curl lets you use HTTP from the command line. So I can curl golang.org. And that returns that same bunch of HTML we saw before, except it doesn't do anything nice with it, right? It just shows it as HTML. Because this isn't a browser, it's just making the HTTP request, okay? There's some flags you can pass. I think -v will show you more details. I went too far. There we go. It gives you more information. Rebuild URL, host name. So this is where it was trying to go to. It connected to it. It's C4080. And then it shows HTTP protocol information, and then it shows the response. But that's the basic ideas. You can use curl to hit URLs, which is sometimes useful because you don't have to use your browser to do that. It's a handy way to download files too, because you can use curl-o and download a file. Okay. So the layer below us in HTTP is either TLS or TCP. TLS is encrypted. We will look at TLS later. TCP, basically TLS is on top of TCP. So we're more interested in TCP. And TCP is the protocol below us. TCP provides a reliable connection. It makes it so that two computers can reliably connect to each other, okay? It's connection oriented, which means that you can detect when somebody connects or disconnects, okay? You're focused on connections. It's reliable and data sent in order. So if I send you a letter and then I send you another letter, you'll get them in order, okay? That matters because remember that packet routing system, that means the second message can get there before the first. Okay? So weird things would happen, right? If I got the bottom half of the page before I got the first half and tried to draw it, that'd be weird, right? So TCP makes it so that they can come out in the right order. So the tool we can use to see that level, I will show you Wireshark, which hopefully works, but is a little spotty on OS X. Wireshark will show you all the TCP traffic on your machine. It is free. Now, if you want to know about the hacker tools, this might be one of them. Okay. Okay. So I'm going to choose. Okay. So this is all the TCP traffic going on my machine right now. And like I said, it can end up being a lot. And so this could be a little hard to work through. What you can do is filter using HTTP. And now it only shows you the HTTP traffic, or it's supposed to. But anyway, I have one open here. It's maybe a little hard to see, but there's a packet, and it shows you the various levels. Okay, so we have right here. It shows all this data. See all these bytes, which are kind of hard to read. But, there's all this hex code stuff. Okay. And it shows you all the various levels, okay? And so, here's HTTP. See, this is UDP. I needed a TCP. I don't know why it's not showing. Oh, probably because I didn't actually hit a page. All this other stuff happening. You know, it's like looking up printers and stuff in OS X. You know, it's possible I'm on the wrong interface. Wi-Fi. Yeah, see, I was only one. I want Thunder Bridge, that one. Bam. Sorry, technical difficulties. Huh. Well, it worked when I did it on Wi-Fi. Maybe it's this one. There we go. Now let's see. There we go. There's all the HTTP traffic. So what I did is I filtered the Ethernet traffic so that it only showed me things that were in the HTTP protocol. But I wanted to show is that HTTP is built out of other protocols. So we see here TCP, Transmission Control Protocol, and we can see the data it uses as part of its header. Okay? And so basically you have TCP, and then inside of that you have another HTTP. So sometimes this is useful to know this information. And there's a bunch of stuff in here. We have the from and the to, the ports, and all kinds of stuff. Also notice we have a checksum here. Checksum, our friend checksum. So every single TCP packet that is sent over the internet has a checksum in it. Like I said, they're super common. So, but anyway, we sometimes have to use, go down this layer. Pretty rare though. The other reason I bring it up is that WebSockets, if you've heard of WebSockets, make it so that you can transform an HTTP protocol request into a TCP one. And then you're kind of, there's a tab in here that lets you see WebSockets, but you might have to go down to this level to see it. And so, anyway, Wireshark, hopefully you'll never have to use this, but it exists if you need it, okay?
So it translates HTTP into what?
The WebSockets takes from HTTP to TCP.
It makes it so you can use an HTTP request response model as like the TCP would. So it turns, HTTP is like make a request and you get a response, and it makes it so that it's more like TCP, which is you have a connection and you can send and receive data on it. People use WebSockets to make it possible to have communication bidirectionally. But
Telephoning.
I'm pretty sure that Firebase's live updates using WebSockets in the background.
probably. Okay. So that's Wireshark if you need to dig into the TCP. Here's Traceroute. Traceroute's another program that we can use. And what it does is it traces that route over the internet. So, and it shows you all the servers it connects through. Sometimes it takes a little while, but puts little stars while it's doing its thing. But it shows you the route that you're taking to get to this website. And so, these times add up after a while. So that's why it takes maybe 100 milliseconds to hit a web page just to get to it, let alone send any information to it, because you have to go through all these various
We're just
routers.
now leaving the college provider just now.
Just going up each level until we finally get to the final server.
Here on campus on.
I think on number 6 where we were hanging, that was Bonnie's office computer.
And what are the stars, Pew?
Oh, there is adding the stars to remind you that it's actually doing something. So they don't mean anything there.
Oh, I thought it was because they couldn't read it or there was some kind of security on the system.
I don't know. I don't know all the,
Okay.
but anyway, this might be the final one actually. Nope.
I like the DCLAX.
Yeah.
I understand that. That's telling me something.
Yeah, that is telling you something, isn't it?
DC Riverside maybe. Baker's Ag 2. I don't know what that is. Fresno Ag. That's about right.
Yeah, so if imagine you plot these on a map and see where the connections are going all over the US and wherever Google
We have
server is.
a drunk router. We're going all over the place.
Actually, you can use the visual trace route and see the locations.
Oh, okay.
There's a web tool called Visual Trace Route.
So there's other things.
That's almost worth a tangent, but there's other stuff, right?
Yeah.
Okay, I talked about packet switch routing, just remember that it breaks it up and moves it around, and so, okay. So that's the basic process of what happens. We look up the domain name, and then we try to send packets to the server that we're trying to hit, because we've got its IP address. And those packets will be using the TCP protocol, okay? And that involves a lot of back and forth. It's like as if you sent a message and then it says, hey, I did get that message, and there's a lot of these kind of communications that happen in TCP. And it does so to make sure it gives you that reliable connection. Once we have that connection established, so we have this connection with the end server, we then start sending HTTP data over it, okay? And then we communicate via HTTP with Google. Increasingly, that's not quite true. Google is in the process of replacing HTTP with HTTP2, which is based on SPDY, S-P-D-Y, which is a protocol they developed to make HTTP faster. So if you use Chrome, it probably, when you connect to a Google server, doesn't even use HTTP anymore. But we still live in the world of HTTP, so that's what we're going to learn. Okay. So what's going on here is, this is modern architecture. This is how most of the software written today has to account for, is networked applications, right? I make a game on a mobile phone, it's connected on a mobile phone to a mobile network, okay? And so we're writing software that's built for distributed systems, right? Everybody get that idea?
Yeah.
It's not enough just to make it run on your computer. It's now got to account for this world we live in of massively network connected computers, right? Even your toaster might be on the internet now. And so we have to write software that accounts for that.
No, it is.
That's not actually far from the truth, as sad as that is. Okay, so the idea is that there are different architectures, different approaches of ways to build distributed systems. There's a lot of different approaches. I'll talk about two that are pretty straightforward. One is the client-server model. In the client-server model, we have a server, which is connected to the internet. All of these work on the basis of things connected to the internet, okay, or just whatever they are. In the client-server model, there's a big server that everybody connects to. And so that's more the traditional approach to web development. So the idea is that I, as a company, say I'm Amazon.com, I have a server that you use to buy things from Amazon.com. Okay? You connect to the server by going to the domain name. That's the client-server architecture. In that architecture, the server is run by Amazon.com, and the client is your browser. Okay? So that's more typical of what we do with web development. Question? No. The peer-to-peer architecture is where, instead of having sort of this massive server, I have two computers that connect to each other. And BitTorrent is an example of a peer-to-peer network. BitTorrent has a server which coordinates the connection between two machines, like two clients, and then those clients talk directly to each other. Okay? Another technology which is just on the horizon is Webrtc. Webrtc allows browsers to talk directly to one another without going through a server. So, as web developers, we're going to have to learn how to do that, maybe. That's in our future. But for now, client-server is the predominant model we work under. And that's the idea that I create a server, people connect to my server, and that's usually how I write software. Okay? The other peer-to-peer would be mobile phones, kind of. Sometimes they can be peer-to-peer, but. So let's keep on this topic of architecture. I showed you DNS, we have name servers, dig. You also use Whois. Whois is kind of fun sometimes. Have you heard of Whois? Yeah. And so you can go look up domain names. I've heard horror stories about some of these sites where if you put in a domain name to look to see if it's taken, they just immediately buy it. So.
You see what?
But it made me buy it, since they see you.
Looking for it.
They'll purchase it.
Oh, yeah.
So anyway, but you can get all this information about any domain name, right? And so I looked up golang.org, and you can see that, you know, the registrars and who it's owned by. No surprise here, it's owned by Google, and et cetera. But, so that's useful sometimes.
Who makes the money on hiding that? Is that ICANN too?
Yeah, some of these providers, some of these registrars will hide the information, and they'll charge a fee for that.
Yeah, it's ridiculous.
Well, they just put their information in there. But hey, I mean, it's no big deal. I have mine stuff in here, right? I mean, whatever. You can see I use Cloudflare for my name servers. I mean, none of this is secret, so it is what it is.
They used to have addresses in there too. Did they put that in?
Yeah, I don't know why it's not showing them. But they're in there, believe me.
They're in there.
Just let me make a note here that if you're watching this video online or anybody in this room is thinking, okay, I'm going to go buy a domain. If you buy your domain at Google Domains, just Google that, they also sell domains. If you buy it at Google Domains, it fits nicely with App Engine and Developers Console so that you could then just plug in, hey, Google, you have this domain, here it is, and they'll map everything. Yeah.
Okay, so we have those two basic architectures, client server, peer-to-peer, and we have this DNS stuff. So we set up our DNS stuff. What does on the server, like, what does that look like? In our company, we're building this web application. What does our stack look like? So the idea of a stack is a collection of software, okay, a collection of software and machines that we use to implement Amazon.com, say. Okay, it turns out it's not just one machine. There's no way there's just one Amazon.com machine, right? There's thousands, if not hundreds of thousands.
I just picture like an old IBM Jeff Bezos closet. I don't know
Yeah,
if
that's
you-
probably it. And so here's the idea of the stack, right? You know, we have the client, the browser over here. You know, you put google.com. That makes that connection. And what is the first thing you typically hit on our side? So this is the stuff we own. So we own this.
On our side, we get a router.
Well, we're on the protocol above that.
Here.
So, yeah, there's routers and things connecting all these, but we're looking at the TCP level now. And so, the router level just makes all the IP.
So we do a request, and we get back a response.
So we hit google.com. The first thing we probably hit is what's called a load balancer, okay? And there are lots of hardware load balancers out there. I think F5 or somebody has one that's very popular. But there's also software load balancers, and a very common one is called HA Proxy. And the idea behind a load balancer is that it speaks HTTP or TCP, but it usually speaks the higher level protocol. It speaks HTTP, and that's what you're hitting directly. And what it does is it fields requests to other servers. And so you might have back here a web server. Now, in sort of more traditional stuff, this might be Apache. It might be Nginx. If you're a Windows shop, it might be IIS. And this is a web server. And this guy speaks HTTP as well. So this guy's sitting as sort of in the middle between the two. Okay? The reason we do that is because it allows us to bring these things down and back up again while not severing the connections that happen up here. Okay? So a load balancer rarely changes. It has rules for routing, but we don't change the software behind a load balancer that way. We're changing our website perhaps every day. Okay? And so the model here is that this is changing a lot, so we pull it out. The other thing about load balancers is it can handle a lot more traffic than a normal website. So this might be a really souped up machine that can handle millions of requests. And back here, we can have more than one. Okay, so we can have a bunch of these web servers. Okay.
And you can check in with each server to see how much it's being used and send
Yeah.
requests to the one that has the most resources available.
Yeah, I mean, there's sophistication like that. Often it just does what's called round robin, which is it just goes in order and flips around. There's an next one. But there's other things you can do. They also often call this a reverse proxy. So the reason it's called a reverse proxy, a proxy is something you might install on your computer, and it would send all the traffic through that application. So instead of going to google.com, you go to this application, and then it would go to google.com on your behalf, and that's a proxy. There's a reverse proxy because it's on the other end. They go to google.com. Google.com actually is fielding that request to another web server. So load balancer, reverse proxy, basically the same idea. Okay.
Is the load balancer where it would find the best based on your location?
It might do that. These things can be pretty intelligent, you know. So there can be cleverness there. There is ability for, I don't know how to do it, but with DNS you can, I think, add information to make it clever about how it chooses where to go. You saw when we looked at Google.com, it had all those A addresses. Normally, it's just going to pick one of those randomly or round robin it. But I think there's some things you can do to make it, well, if you're in this region, go to this one. I don't know how quite all that works. Services like Cloudflare will do it for you. So you can just use Cloudflare and it'll take that out of your hands. Okay, so we have our web servers. Normally, with web servers, you don't usually run everything on one machine. You're going to have another machine, say over here, and this might be a database. Okay. So these web servers are talking to a back-end system as a database. So we might call these front-end systems and these back-end systems. And these could be databases, they could be mail servers, they could be anything. Okay. And usually different teams are working on different ones. Small startup, everybody does everything. But in larger company, the team that's responsible for this is probably operations. The team that's responsible for this is probably a front-end web developer. The team that's responsible for this back here might be a dedicated SQL person, SQL database person. It might be just a back-end team. Okay? And also operations would be involved in that too because they're setting up hardware. So, but that's the basic architecture is you have your load balancer, you have your web servers, and then you have your back-end systems, which could be databases, mail servers, etc. Increasingly, there's also a third thing here, and we'll call that the cloud. And so these machines will get them as well. Okay. So if this is the we own box, these are kind of outside the box. So these might be machines that are like physically in your building. Okay. You know, you have a data center and they're sitting in there. This is somewhere else on the internet. And you're connecting over the internet to these cloud services. So, for example, you can get a MySQL database from Google. You pay a monthly fee for it, and you can connect to it from your servers. Okay? You can also create those servers in Google's infrastructure. So I can get a virtual machine. That virtual machine is running in Google's cloud data center. And then the two can talk as well. Okay? And so they have different levels of how much control you want. But the idea is that you have these cloud services that also fit into the web architecture. Okay. The final piece of this I want to talk about is also a very common pattern. And that's a queue. Does anybody know what a queue is?
Bring you.
That letter after P.
It's like a list where they start lining up.
First in, first out.
So sometimes it's useful to have a system where instead of pushing it to the back-end system, you push it to a queue. And a queue is a line. Okay? It's a thing that will hold messages in the order they're received. And then, actually I should draw the arrow the other way. Okay? And then there's a back-end system that pulls messages off the queue and processes them. Okay? And so this is a very common pattern as well for web pages, for web applications, is that my web application pushes a message onto the queue, and then there's a backend system that's pulling messages off of the queue and does stuff to them. And what's nice about this is it makes it so the web system doesn't talk directly to the backend system, which means they're decoupled, which means it's easier to control the two without affecting the other. Okay? And to give you an idea of the architecture, GitHub has an architecture like this. There's a website that shows stuff. And then when you say, add a new project, it involves pushing messages onto a queue to set things up on their server. Like checking files out and all that kind of stuff. And there's back-end systems listening that pull those messages off and do that. Okay? And so they use a system called Rescue, which is built on top of a NoSQL database called Redis to do that. Okay? But the point is they're using the queue architecture to do that. The idea of having that middle layer system in between the two. Okay? And so that's a very common pattern as well. We'll see that a lot. So that's basically architecture 101 for web apps. What we're making is this layer. We're basically building this guy. Okay? And that's what we're interested in. Everybody following? Any questions about that? Okay.
Holy cow.
I think drop right